So, yeah, so the title, I think that's the public title of the talk, or how to have fun with the summary statistics tables of your papers that you read. I like to start all my talks with this now. And the reason I'm putting this up is that this will not always be the case with people who are giving talks that you attend. So I'm getting reimbursement of my second-class rail travel and my hotel room at in the opulence of the Premier Inn in Brixton. None of this research was funded in any way, and I do not perform paid consultancy on any of the topics discussed in this talk. You will go to talks where people are getting paid 4 and sometimes 5-figure sums just to be there. I know of one American psychologist who requested to go to a conference and give a keynote, 50,000 US, and return air tickets to Australia for himself and 5 members of his family first class. So, you know, a lot of money in this business. So, yeah, what about, I'm old, so that's how old my bachelor's is. And that's 30 years later, I went off and did a master's and converted myself into something resembling a psychologist, I guess. How many people here are in psychology versus, yeah, how many would say they're psychologists? Okay. And the rest biomedical or psychiatry? Okay. So I got my PhD. I was offered 2 possible days for this talk. One was the 31st of October, but firstly I wouldn't have had my PhD then, and secondly the next day going home, I live in France, would have been no-deal Brexit day. So I postponed that to avoid travel chaos, and I don't know if you've seen the news this morning, but France is currently in total travel chaos, and my Eurostar has been cancelled, so yeah, you never make the right choice. So yeah, in between the bachelor's and the master's, I spent 31 years in IT and management, and then in a terrible administrative mix-up, I was moved to human resources, none of it in academia. I actually read my first scientific paper in 2011. And I am very poor at PowerPoint slide design, which you'll be getting to see as we go through. Okay, so what is the problem that we have to address? Well, published articles contain lots of errors. You read an article, as a minimum, you're going to find 3 or 4 typos. I mean, don't people even proofread their stuff? And even in top journals, you know, when you get published in JPSP or Nature, read the damn proof. And we all see things that, how can that be right? Have I read it properly? Have I understood properly? That doesn't look right. And you might want to write to someone and say, can I have a look at your data set? But it's incredibly hard to actually get data sets out of people. And I mean, I've been in situations where people have posted a public data set and then we pointed out an error in it, and then they uploaded a corrected version of the data set without telling anybody, so that anyone who then read our critique and downloaded the public data set was no problem there. So people are pretty devious, and those 2 references from 1962 to 2006 both show that about 40% of psychologists will share their data with you and the other 60% won't, which is pretty poor. So sometimes it's just you and the PDF and some feeling that something isn't quite right here. And so what I'm going to show you today are a couple of techniques that we have semi-formalized to enable you to look at various aspects of the statistics of a paper. They all have terrible names. So first up is something called GRIM, which stands for Granularity Related Inconsistency of Means. So it's about means that are inconsistent with the sample size. And the inconsistency is detected by the fact that what we call the granularity, you'll see in a minute, is not possible. So, yeah, not all mean values of integer data are possible. In psychology, we're often dealing with integer data, but you can have that in other fields where you're dealing with count data. So if we ask a bunch of people, 7 people, and we ask them how many children do you have, then between those 7 people, they might have 10 or 11 or 12 or some number of children. And if they have 10 children, between them, the mean number of children is going to be 1.43 or 2.43. It's going to end in 4.3. And if they have 11 or 18 children, the mean is going to end in 0.57. And this is fairly intuitive. And most people can do this in their head up to about 9 or 11. But it turns out that for any n less than 100, and we're working with 2-digit means here, n% of the means are what we call consistent, Grimm consistent, and the others are not. So here, for example, if you were to see that the 7 participants reported having a mean of 1.52 children, you would know there's something wrong there, because they can't have 1.52 children mean. If you multiply the 1.52 by 7, you're not going to get close to an integer. So, how do you check this? You can use a calculator, or I tend to use an Excel sheet, but I built this little microsite, and so this is the only time in any talk this year where you are actually invited to open up your web browser, and even on a phone, it's a tiny, it's not an app, it's a website, it's 6 lines of JavaScript. You have to type Grimm in uppercase, and that's how those of you who've got it up, that's how simple it is. And you just type in the numbers and it'll tell you whether it's consistent or not consistent. I sent Sam a draft of the slides, but this is a slightly updated version, so I'll send you the full afterwards, and you can get the slides from Sam. Okay. And let's describe how you go to a talk now, and someone's presenting their data at a conference, and you sit there going, oh, really? Oh, that's interesting. Oh, just one more thing. You know, Lieutenant Columbo. Okay. So, for example, reported n of 28 and a mean of 5.22. Is that consistent or not? Well, how would you do it by hand? With a calculator, you'd multiply those two numbers together. You'd get 146.16. So there might be rounding. So the nearest integer is 146. So that implies that between, let's say it's children again, a lot of children, but these 28 people say they've got an average of 5.22 children. Do they have a total of 146? Well, if we divide 146 by 28, we get 5.21, and that should round 214. That should round to 5.21. So that's not consistent. This is 5th grade arithmetic. We submitted it to a journal, and we expected them to laugh at us, and they actually asked us to make the math simpler. What happens if you have multi-item scales? The range of the responses, so if you're looking at a 1 to 5 or 1 to 7 or a 0 to 9 Likert type scale, that doesn't matter. It's completely irrelevant to Grimm. It's simply the number of items. Because again, you can use open-ended count data. So if we have those n equals 28 and we have a 3-item scale and a mean of 5.22, that's actually equivalent to having an n of 84. Because we multiply up, and that will be the total number of whatever the integer response means, 438.48. We round that to the nearest integer. We divide it by that number, and again we come out at a number that is not consistent. Now, if you've only got 2 decimal places, this can quite quickly overwhelm your ability to use this system, because if you have the number comes to over 100, any of the numbers are possible. But sometimes you have 3-digit reporting, and sometimes you have very small sample sizes. So the limitation, big limitation on this in many cases is if it's a big study. But a lot of the studies in psychology use quite small sample sizes. So what might cause Grimm errors? I always say Grimm errors, and then I always have to cough and say inconsistencies. All we can say is the numbers are inconsistent. So sometimes you're reading an article and the mean doesn't add up, and it turns out that on one particular item 3 people didn't respond, but they didn't put that in the article. So the n isn't what was described. Should they report that? Probably, but sometimes they either don't report, or more often you reading it don't notice it was a multi-item measure. That happens quite a bit. That's embarrassing. There is a phenomenon of double rounding. If those use SPSS, who uses SPSS? Oh, quite good, not me. SPSS by default reports almost everything to 3 decimal places. So if you had that number, 3.24715, SPSS would round it to 3.245, and then you go and read that off the page to round it for the journal, and because you've been taught to round 5s up, you would round that to 3.25. But in fact, if you rounded it directly from the 6-digit number, you would have 3.24. So that's one of the things that we found when we were researching this. Sometimes you get halfway values. People are filling out a pencil and paper questionnaire and they circle 2 answers. What do you do with that? Are you going to discard an entire participant because they couldn't decide between 3 or 4? Why are you coded as 3.5? I've seen that done. That happens more often than you'd think. Errors in data set handling, just things getting moved across columns or people doing their analyses in Excel and picking up the wrong range of data. That happened with a fairly drastic case that we looked at. Or, and this is more interesting, occasionally it is a phenomenon that we give the medical sounding term of proctonumerology, which I trust most of you can work out what we mean there. And so this whole talk is about errors, but sometimes the errors are not accidental. Sometimes you can have a whole bunch. Let's have a look at this. I'll show you these numbers, and I actually made them up, and it gives a perfect. So here is some means from 10 single item measures, from 10 samples of n equals 41, and these are the reported means. Now, I don't think many of you are very good at dividing by 41 and doing modulo in your head, so that's why you would have the calculator. I just wrote those numbers down completely at random and checked them, and I was really lucky because the chance of any random 2-digit decimal fraction, let's imagine I'm just totally fabricating this data, and I'm going to go, 1.23, 4.69. The chance of any of those numbers being consistent by chance is 41%, because 41 of the possible fractions are valid and 59 aren't. And what was interesting, I made this up, and those 6 are not valid, and those 4 are valid. So if you were to see that, the chances are that probably all of them have been made up. And because 4 of them are going to be hits by chance. So if I saw that in an article and I had other reasons to suspect that there was dodgy stuff going on, I'd be interested in that. What happens if you have 80 and 20% of the means are inconsistent? That's a little bit more difficult. But certainly when you have a small sample size and lots of inconsistencies, and particularly if you say, okay, what happens if n was 40? Do they work? What happens if n is 39? Do they work? The authors as a minimum have some explaining to do. Why do these numbers, this number is not what you get when you divide this number by that number. Dear author, please can you send me your data or explain what's going on? Okay, so there are a lot of limitations of GRIM. This is not a major fraud detection tool, but it's a very early sniff test for problems in a paper. First of all, it's almost impossible to automate. Because of our reporting standards and lack of metadata, you have to read the article and fully understand it. It's actually a good way to understand a method, to read and try and do the GRIM analyses and work out exactly what numbers were in various columns in the data set. You have to read the text really closely. And some people report in sentences, some people report in tables. Sometimes the sample size is at the beginning of the methods section, and then halfway through the results they say 2 people were excluded because they had too much to eat at lunchtime or something, and it just gets... what was the actual number going into this calculation can be very hard to work out. Now, it shouldn't be that way. We should be, well, first of all, we should be supplying the data, but we should be writing our articles in much more structured ways with metadata. But, you know, the reporting formats and standards were designed in the 1950s. Well, typically limited to a small sample size or a smaller sample size if you have multiple items. But you'll sometimes see percentages of 23.7% of people will, and that will work for a sample size of 1,000. It's amazing how often the percentages of ethnicities don't add up to what was written. And then you look and you twiddle around and add one and take one off and go, okay, they got this one wrong. And yeah, in psychology you have small sample sizes, so it needn't be too much of a limitation. So yeah, we got an article out of this. We took 260 articles from 3 top journals in psychology from 2011 to 2015. we were able to check the statistics in one or more statistics in 71 cases because the sample size allowed us to. 36 of them, of the articles, we found one or more inconsistent numbers. Of those, 21 of them seemed to us to be sufficiently serious that it might have affected the results. We wrote to the authors. We got 9 data sets. That's pretty much par for the course. All 9 had genuine reporting errors in it of some kind. And we got 3 corrections issued. There were also a couple of cases where we are fairly certain that the entire article was fraudulent. So, just from randomly going through a bunch of articles, half the ones we were able to check had at least one inconsistency. And these are people who are and even the honest, there are very few typos. Very few of these were caused by typos. Some of them were caused by missing people in the sample. But in the, you're getting, these are flagship journals. You'd expect people submitting to them to really put a lot of effort into getting everything right. And it was quite disappointing. So here's an exercise for you. So it's pretty straightforward because n is 20 in each case. So can you find the grim inconsistencies in this table? Start playing the countdown music. Anyone? You don't need the calculator.
The ones that end in 5 or 0. Yeah.
Pretty much, yeah. So this one. And what's interesting is it doesn't work if n is 19 either. Maybe one person didn't answer that question. These only work if n is as low as 13. Kind of 7 people missing out of 20. Even if that were the case, you've got a bit of a problem. Okay, this is not just any random paper. This is from, the psychologists here have probably heard of this paper. This is the original empirical validation of the phenomenon of cognitive dissonance by Festinger and Carl Smith. This paper has citations into the thousands, and this is only one of the visible from space issues with this paper, which Matti Heino wrote up on his blog. It is a horrifically bad paper in many, many respects. The authors are no longer with us to explain what went on, but this is truly horrific. It's interesting to watch people dealing with the cognitive dissonance of their cognitive dissonance paper, not... So, this is all there waiting for you. And this, So if Festinger and Carl Smith can get it wrong, you can imagine what people are getting wrong in some lesser journals and some lesser articles. So, all right. Questions at the end or questions after each chunk?
I don't know. I mean, it depends.
Anyone got a question at this point?
Does anybody have any questions?
Yeah, very interesting. The replication crisis seems to be hitting different areas differently. In that social psychology is turning out to be basically no good. Whereas other areas like personality research have turned out to be more difficult. Have you found with your grim assessments that you could have predicted that?
We didn't really, we were going through them so quickly we weren't even looking so we didn't make any sort of reference to what the subject area was. So psychological science will have covered everything. Journal of Experimental Psychology General covered most things. JPSP. I couldn't really tell you if there are more problems in social psychology than...
Well, there obviously are. So did you pick it up?
Discussions of the replicability crisis up till now have mostly focused on things that we're more prepared to talk about than this. This is kind of another layer around it, and it affects things beyond psychology as well. What do we call cognitive dissonance? Do we call that social or personality psychology?
Well, social psychology, obviously. Because it doesn't hold up.
Yes. I do notice that, I mean, I've only arrived since 2011, and I do have the impression that the period from 2011 on could be called Revenge of the Nerds. And the personality psychologists are sort of finally getting their own back after 25 years of being, yeah.
Yeah, I'm a nerd.
Could you just repeat, how many did you say that you thought were completely fraudulent in that study?
How many did I think?
Were fraudulent?
At least two. At least two. At one point, we wrote to several of the authors. Three of the authors wrote back and outright refused to share their data, not drag their feet, not claim to have lost it. They just refused. And two of those three letters were identically worded. We actually went on Google to see if there's a website called howtoblowoffpeoplewhoaskforyourdata.com, full standard letters that you can send to people to tell them they ain't getting your data. And one of those two came from the corresponding author of a team that included a person whose name I won't mention on the microphone, who has been accused credibly of multiple counts of research fraud. But there were others too. There were at least two you could see. There was the case where the corresponding author's email address bounced as non-existent, which happens, but not very often with Gmail. And they deleted their Gmail and got off the grid. Their previous institution did not have a forwarding address for them.
And what did you do with those papers? I mean, in terms of the write-up, what did you do?
Sometimes we blogged about them. Sometimes with that one, I went to the editor, and the editor said, "Oh, it was 2011. He's got too much stuff on his plate already." I mean, it's just they don't. The editors either ignore you, or they have so much on their plate dealing with this stuff that it comes to a point where they could just spend their whole life correcting stuff and they would never actually publish anything because they'd just be correcting errors. It's really bad. It's really bad. Okay, so SPRITE. SPRITE is another horrific acronym. This is my, as Sam described, partner in crime, James Heathers. This is one of the better pictures of James. James is my height and about twice as wide and Australian and, loud. So we were doing some grim works with means. It can sort of do stuff with standard deviations, but it's very tedious to do. So James came up with the idea of seeing what possible means and what possible data would match means and standard deviations automatically. So you input to SPRITE a mean, a standard deviation, a range, which could be the limits of your Likert scale, but they could also be, for example, participants ranged from age 13 to 27, and a sample size, and it will generate, heuristically, a set of possible distributions of those values. It's quite nice if you ever want to generate a data set that has an exact mean and standard deviation. Those of you who use in R, you might say R norm and specify a mean and standard deviation. But if you actually look at the standard deviation of mean, it won't be exactly the same. It attempts to do it. SPRITE will give you an exact mean and standard deviation that match to however many decimal places you want. So one use is to generate that data set, but the most interesting use of SPRITE is to take values like that and say, I wonder what that data might look like, those data might look like. So, for example, we've got N135, a scale from 1 to 9, mean of 4.8, standard deviation of 1.7, and here are just some of the distributions. All of those distributions have exactly that mean and standard deviation. You can generate 3 by 3 or 10 by 10. So there's a central tendency. And when you've done enough of these, you can start to do, you don't even really need to generate it because you can start to imagine it if you're with, particularly with Likert type data. So now, let's say we're reading an article, but instead of that, standard deviation is 3.4. If you can imagine, form a little guess in your head as to what that looks like. So this is what you might, now, is this reasonable? Depends what you're looking for. If you're looking for some kind of normal distribution, no. But if you went out in the street and said to people, how do you rate Donald Trump or Brexit on a scale of 1 to 9, you wouldn't find it unreasonable to have that kind of polarization. So it just gives you a quick way of saying, I wonder what possible, in this one, the 1.7, there are lots of possibilities, but you can see there is kind of a central tendency there. It's heuristically driven, so it generates random samples until it finds something that matches. As a result of which it's quite quick and doesn't have sample size limits. It can sometimes be a little bit imprecise, but most of the time it's pretty good. It does not guarantee that a solution will be found if one exists, but it mostly does find a solution if one exists. Round about the time we were working on this, these people were working on a solution that actually generates the complete solution. Now, with n equals 40, that's great. You can do it on your own computer. When n is like 600, you need to phone up the Met Office for the weekend and ask if you can borrow their supercomputer. But you can get a complete solution. It's just, yeah, very compute intensive. You always have to interpret the results in the context of the study, in the context of what the variables mean. So like I said, if you've got that split like that, if you're asking a fairly controversial question, that might be reasonable. If you're asking, you can see whatever the distribution is like, and would that distribution be something that I would find reasonable? So let's have a look at a practical example of SPRITE. So this is from an article by a French psychologist called Nicolas Guéguen, who has over 300 publications. He's only got one retraction so far, but there are plenty more coming. You can find descriptions online of some of the controversy about his work. So this is a study in which, allegedly, students or participants went into a room and answered questions, 4 questions or 8 questions, I think, on their belief in global warming. And the manipulated variable was that they were filling this questionnaire out at a table, and on the table was a ficus plant that was either dead or alive. And the idea was that if they were in the presence of a dead plant, they were more likely to endorse beliefs in global warming. And so this is an example of one of the questions that was asked. It seems to me the temperature is warmer now than in previous years, on a 1 to 7 scale. So in the presence of a live plant, the reported mean was 5.1 out of 7, and the standard deviation 0.6. And SPRITE returns about 20 solutions, between 20 and 25 possible solutions. And they all look pretty much like this, which means most of the people are responding 5. Now, I don't know about you, but if you take 18 and 19-year-old French undergraduates and ask them if they believe in global warming, I'm going to guess 1 or 2 of them will normally, more than 1 or 2 would reply with 7. It's a fairly straightforward question. There aren't even any contrarians. In the presence of the dead plant, the mean went up to 5.6 with an SD of 0.5, so we can see there's a Cohen's d of about 0.9. It's an effect. We can make people believe in global warming more by exposing them to the terrible climate-induced consequences of not watering your office plants. That's what the results look like here, and there are only 3 solutions. I've only shown 2, but there literally are only 3 possible solutions. And again, even in the presence of the dead plant, oh my God, the world's coming to an end, nobody has answered 7. So, yeah, you can place your own interpretation on that. I haven't got the website for SPRITE up on here, but if you want to have fun with it, if you have a look through my Twitter feed, you'll find it, and I'll send it on request. So, that's a very simple example, but you can do some interesting things with SPRITE when you're looking at data and going, how would that have looked like? Okay, any questions on that? All right. So, RIVETS, another terrible, terrible name. We have to kind of come up with a one-word acronym for these. If you have rounded input variables, you will get exact test statistics. This is a little bit, you have to pay attention for this one. So, let's have a look at always trying to prove in psychology that pigs can fly, and we have our own journal. So this is a typical sentence you would find in a psychology. Pigs in the self-piloting condition ate more kilograms of feed, blah, blah, than did pigs in the drone transported. So we've got a sample size, we've got a mean, we've got a standard deviation, and we've got a t-test. And we might want to say, okay, do those numbers add up? So we would go to our online t-test calculator. I don't know, I'm sure some of you have seen this, or you might have your own little personal Excel sheet with the formula in it, but the online calculators are quite handy. This one is at graphpad.com. Anyone used it? Yeah. So you choose, okay, I'm not going to type in the data, I'm just going to enter the mean and the standard deviation, and you enter those numbers that are here, and do the unpaired t-test. Of course, you should use Welch's t-test, but we're doing what the authors did, so. And you do the calculation, and yeah, so this difference is extremely statistically significant. We don't say extremely statistically significant, so we'll cross that out. But here are the numbers. So there's the t-test result. There's the degrees of freedom. That was what was in the article, and you can see that those are the same. But we put in the exact rounded two-digit means and standard deviations that were reported from the paper. Now, those numbers didn't have to be those numbers. For example, so here are the numbers that were reported in the paper. That mean of 4.53 could have been this. That mean could have been this. These standard deviations could have been that. These are some extreme values, but they could have been there. And if you do that calculation, you end up with a t of 4.09. And again, we could have had these numbers. They again round to these numbers, and we do that, and we would have had a t of 4.23. And so those numbers are summarized here, and I can add a couple more. So any of these numbers, being the sort of internal numbers inside the computer when it's doing the mean and it's doing the standard deviation, and obviously they'll be able to get far more decimal places there, would give you those t-statistics, even though all of these numbers will round to what is in the article. Now let's imagine that you didn't actually have any data because you never ran the experiment, or maybe you ran the experiment and didn't like the results, so you just made up some numbers. You would probably make up the mean, you'd make up the standard deviation, and then you would go off and do the t-test, and you would end up with that exact result of 4.09 because you were putting those rounded numbers in there. So, this is really to read when you get the slides later. So the software, because the software only rounds at the end of the calculation process, when it prints out the mean and it rounds everything at the end. The unrounded means could have been any of these numbers. And the central value, the 4.16, is typically the most likely value that you would get if you had real unrounded numbers that you hadn't cheated with, but it's not necessarily very likely. So we can do some simulations. I did some simulations using numbers that rounded to those values, and that between 4.1501 and 4.1649, only 16% of the area is in that column. So the chance is that arbitrary means and standard deviations that round to those reported values would give you that exact t-statistic is about 16%. In this case, it varies enormously in every case. Now, if you see just one number, that's fine. There's a 16% chance, that's fine. But if you have 15 values in the article, and they all correspond exactly to what you would get if you just made up the rounded numbers and done the t-statistic, then you've got the author has some questions to answer. So we have to use we have to simulate each time. There's no simple formula for doing the simulation. So here's a real world example from an author who has just had 5 articles retracted, none of them this one. Those articles are from 2011 to 2018. So this is an article of the same author from 2003. Now, in this case, we're constructing, this doesn't have to be t-statistics. There are plenty of other statistics that are derived from two other numbers. These are t-statistics, but they're from regression, so instead of being mean and standard deviation, they're simply the regression coefficient divided by the standard error. So here is, and it's helpfully reported to 3 decimal places. So the coefficient 0.941, the standard error 0.019, so we put that into calculator, and so that's the reported t-value from the table, that's the calculated one. You'll see they will round to the same number. The next one, 0.212 divided by 0.013, 6.83, so 87 rounds to 6.839. So those two are identical. So it's a bit boring doing it in the calculator, so we do it in Excel, and you will see that every single one of those is identical. And there are 3 decimal places reported, and so the chance that any given number would come out like that by chance is pretty small. You can see there are some small numbers there. And there are 2 tables like this in the article, and the results are all identical. And if you multiply all of those probabilities together, that's a probability, not a p-value, you end up with a joint probability of somewhere in the region of 10 to the minus 41. Yeah, those numbers exactly the same the whole way down. So, now, maybe the author did those regressions and printed out the numbers, and then the computer crashed and they lost the data, and all he had was those printed out numbers, and then he had to go and compute the t-statistics. I'd like to know. I'd like to know what happened. Because generally, those numbers come out of an analysis program, and your biggest problem is getting the formatted text and pasting it and including the tabs so that you can put it into a tabulation program or Excel or something. So yeah, that's just based on the observation that the exact value typically, or the t-test, or the final statistic typically won't be identical to what the input numbers would suggest, because the input numbers typically are not rounded before the computer does the calculation. I recommend getting the slides and reading them again, because it's a little bit, it becomes second nature after a while, but this is not something you're going to get first time, I think, in 10 minutes. Okay, so that was GRIM, that was SPRITE, that was RIVETS, and just a kind of overall caveat slide. And we have other tests like this, some we're working on. You often can't use these techniques. In fact, for any given paper, in 95% of the cases, you can't use these techniques. But there are useful things to know. Oh, maybe I can test that with this. Maybe I can test that with this. For example, if you have within subjects results where the individual data points really matter, it's quite limited as what you can do. The worst written articles are the hardest to investigate, because they will contain all kinds of ambiguities about what the method might have been. And it's unfortunate that the people who are incompetent at doing their stats tend to be incompetent at communicating their method. And so you could potentially end up writing 15 times, yeah, but what did you do exactly? And then what, and the most parsimonious explanation for everything, possibly with the exception of a RIVETS sequence like we saw, is an innocent mistake. So none of these are, grim inconsistencies are not reasons on their own to write to the editor and demand retraction, and write to the author's university and demand disciplinary procedures. But that said, a grim inconsistency is a grim inconsistency. Those numbers are right there on the page, and obviously you get someone else to check them for you, but that should not be happening. That sort of thing should not be happening. And as a minimum, it should probably be corrected. Now, are you going to bother writing to the editor for one tiny thing? Maybe not. But actually, you can have some interesting discussions with the authors. Hey, I read your paper, I found this. Are you sure this is okay? If it doesn't, and they'll say, oh yeah, I think that was the one where we excluded 3 of the parties. We should probably have written that up. And you write to them in an open and friendly way, and you'll usually get, if it's a genuine error, you'll usually get an open and friendly response. I've had people write back, oh my God, my paper in JPSP has a tiny error in it. I must. And going, well, don't beat yourself up too much. It's really, so we don't want to drive authors to kind of, you know, do anything drastic. But you can, if it's an honest mistake and you're nice about it, if they write back and start, or they don't answer, or they start being defensive, then we start looking, oh, I wonder, what about their previous paper? Let's see if that's got any, oh, that's interesting. So, again, I'll get the slides to Sam. We've got the full references. So I have a Twitter is the best way to get to me. I have an email. I have a blog which I tweet about anyway, so that's redundant. That's my Google Scholar profile. I never liked having 3 given names, but it's been really useful because there's a lot of Nick Browns out there, but I'm the only Nicholas J.L. Brown, and this is the point at which Jeb Bush famously said, "Please clap." Discussion.
Thank you. Thank you very much. Questions? Any questions? Yeah.
You said that 95% of the time you can't use these methods on but for the other 5% of the time you can, do you always apply methods? Or
When I'm reviewing, I do now. Yes, absolutely, absolutely. It just becomes a kind of mental habit. And even when I'm not reviewing, you'll look at and as I say, there's so often Grimm or other inconsistencies just in the demographics, just in the mean age of participants. Now, given that most participants report their age as an integer, it's very weird. I don't know why we do that, because you'd have thought a tenth of a year might be valid. But how old are you? 27. And you look, and the mean age of the participants isn't right. Or the percentage of 72% of the participants were, and you go, that percentage is impossible. I had one the other day, and it was 92 parts. I remember the numbers because it was 92 participants, 23 brackets, 75.9% were men. But I don't know. I mean, 23 goes into 92 exactly 4 times. Maybe I'm kind of a little bit nerdy for knowing that. You know, it's 75.0. Why have you written 75.9? Could be a typo, but it occurred twice in the paper. So was there a different sample size, and you kind of fudged it, and then you went back and you didn't, you only unfudged one of the numbers and not the other one, which happens, I think, probably quite a lot. So it does become a little bit of a state of mind, yeah. And I don't get the calculator out necessarily every time, but it's surprising how often you find Grimm issues.
So you don't wait till you smell something fishy about, like, this is an impossible result, or I don't buy this now, I'm going to start grilling it. You just instinctively start to look at the table.
Yes, I mean, after a while, just to say, I've done enough. When you've read 260 articles and scanned them, and by the end of that was like over Christmas and New Year. One of the things you find very interesting is how all JPSP articles are basically the same. You could, if you had to write a bot to write articles, these people write these bots to write computer-generated articles, but I suspect JPSP articles probably are written by a bot because they're so formulaic. So yeah, you get into that, and then sometimes distribution of ages of participants. I'll put that into SPRITE and see, okay, so you said they were aged 13 to 77, but according to this, most of them must have been 13. Now, maybe that's legit, but you should probably have told us that 2/3 of the participants were 13, and that you got one old person, rather than giving us the impression that there was some range.
Any other questions? I have a question. Have you noticed, I don't know how many times you've applied Grimm or SPRITE or RIVETS, if there's any relationship with the year the paper was published?
No.
So, for example, because the idea is that significant null findings are disappearing from the literature paper, and I just wondered whether there's an increase in these errors that are being reported, or a decrease because we're supposedly using more sophisticated psychology.
I don't think in psychology that there was a golden age in the last 50 years where we were publishing more or less valid results, or we were doing more or less harking or p-hacking. I think it's a fairly noble tradition. If you look what people like Paul Meehl were writing in the 1960s, and that the classic article called, is it Trouble in the Brickyard or something in the Brickyard? A 1963 article about how people are just basically generating papers for the sake of it and not actually contributing to theory. Yeah, 1963, and they're just building bricks, but we can't, they're all different. We can't take these bricks and make a house. I certainly haven't done, you know, any sort of quantitative coding up of this. Doing large amounts of analysis with Grimm is pretty tedious. You know, you've got to read the article quickly, understand it, and apply the right sample sizes, and that really does require quite a lot of effort. So bulk. I had a poster, or I was on a poster because it was presented in the US, and we attempted. What happened was somebody took one or two of the replication projects, and we attempted to see whether the prevalence of Grimm and other errors in the original predicted replication success. And it didn't, it was flat as a pancake. With a sample size of 150, but only which 30 or 40 which had Grimm problems anyway, and so, you know, the actual effective sample size was quite small. So I don't think there's any, I think it's a combination of remarkable inattention to detail when reporting, and a baseline prevalence of fraud, which I think everyone has their own informal estimate of.
What would yours be?
I don't know. I asked Yuri Simonson, who's investigated a lot of fraud cases, has gone on record saying he thinks about 5% of psychology papers are fraudulent. I asked a few colleagues not what they estimated the prevalence of fraud was, but I asked them, if you were to discover that the true prevalence of fraud was n%, for what value of n would you be kind of surprised? You know, I didn't think it was that high. And the mean of that was about 15. But big range, big range. So I think there's quite a lot. I think there's quite a lot of fudging. If you look, the temptation is high. The rewards for doing it are quite high. The chances of getting caught are almost negligible. Yeah. We actually know from, you know, many years of social science that when, or economics or criminology, that when you combine, you know, high incentives for doing the wrong thing, low incentives for doing the right thing, lots of ample opportunity and minimal chance of getting caught, you know, we know that you don't have to draw pictures. You know, it's so, I wouldn't be remotely surprised, and I don't think we should be remotely surprised if there's a great deal of fraud going on. I would be surprised if there wasn't under those circumstances, because science is carried out by humans, yeah. and most of them are not sort of, you know, Gandhi or Mandela types. You know, most of them are ordinary people who otherwise would have a job in industry or whatever and have mortgages to pay, and are quite interested in the continuation of their monthly paycheck. There is a big, the reason why most of the reform movement in science is being conducted by grad students and postdocs is that they are not yet enjoying the remarkable ease in life that comes with a monthly deposit in your bank account in reward for basically going along with the organisation. Whatever walk of life you're in. You know, life is about life. Modern life in the Western world for people over 30 is hopefully about going to work, getting a regular monthly deposit in your bank account, and not causing too many waves for whichever particular organisation you happen to pledge allegiance to. And that's just the human condition, I think. And I don't think academia is very different, or science in general is any different from any other kind of field of human endeavour in that regard. I'm quite pleased that my 30 years of working in private and public sector outside of academia sort of prepared me for people going, oh, this is so corrupt. It's like, mate, this is life. This is what having a job is about, you know. Oh, senior faculty harass the staff. Yeah, bosses harass the staff everywhere. This is probably, there will be specifics to the academic environment, But, you know, the fact that the Vice-Chancellor has a helicopter or whatever, you know. I like the story of the guy who comes to work one day and his boss comes up in a new BMW 5 Series and parks right up by the door, and he says, "Oh, nice car, boss." He says, "Listen, let me tell you, you work hard, keep your nose clean, and next year I can buy an even better one."
Well, on that depressing joke, any other questions? Oh, well, thank you very much. I'm very, very thankful that you made it all the way over here from Strasbourg, and I hope you...
I'm swimming the channel back, so...
Swimming, I'll enjoy. So, a round of applause.
When does the riot start?
Well, we've got tea and coffee out there.
Oh, well.
So
Yeah.